Our next speaker is Briana Schmidt. She's a group leader of energy and carbon management at Lawrence Livermore National Lab. She's also the PI of the first and largest of its kind DOE-funded field trial of carbon mineralization of ultramafic mine tailings at a former KCAC asbestos mine in San Benito County, California. Her topic today is carbon mineralization in California. Welcome.
Hello. In addition to all those things that Leosha just said, I know I'm also the thing standing between you and lunch, so we will keep this snappy. So I'm going to talk about carbon mineralization in California, the opportunity, and some research that we're doing at the lab. So carbon mineralization, for those who aren't familiar, seeks to speed up the process of chemical weathering. So chemical weathering is a natural process that transfers CO2 from the atmosphere into carbonate rocks where it's stored over long time scales. And so just briefly, CO2 in the atmosphere interacts with rain or surface water, dissolves in rain or surface water, which forms carbonic acid. That acid then reacts with the rocks to break them down. Carbon is carried by rivers into the ocean, where that carbon then reacts with things like magnesium and calcium that have been released from those dissolving rocks to form new carbonate minerals. And then over geologic timescales, those rocks eventually get subducted under volcanoes and the CO2 gets released in volcanoes. So this natural process balances itself over geologic timescales, but we want to speed it up in order to pull more CO2 directly out of the atmosphere. So there's 3 rate-limiting steps in this natural process. One is the CO2 supply. I have to stand on my tiptoes to see my slides. And even though, human activities have added a lot of CO2 to the atmosphere, the concentration is still low, as we've talked about in the context of direct air capture. The second is the rate at which minerals dissolve, the rocks dissolve, and the third is the rate at which those new carbonate minerals that contain the CO2 form. And so those 3 things are all dials that we can try to turn in order to speed up that natural process. So the types of rocks that are best for this process are ones that have a high proportion of those things like magnesium and calcium that we can use to form those new carbonate minerals, minerals that dissolve rapidly from contact with that carbonic acid, and ones that form stable, solid carbonate minerals that are going to be stable at the Earth's surface and not redissolve and release the CO2. And so generally speaking, the types of rocks that are best for this fall into 2 broad categories known as ultramafic rocks and mafic rocks. So these would be things like peridotite, pyroxenite, basalt, gabbros, and the metamorphosed version of some of those rocks known as serpentinites. So these are contain minerals like olivine and pyroxene that have high concentrations of magnesium and iron to provide those elements that we need to form those solid, stable carbonate minerals. The good news is that these rocks are all over the world and they are abundant. This is a map showing those 2 types of rocks and where they occur. So there is, in theory, many more times of this rock available to remove all of the CO2 that's ever been released by all human activities if we can figure out how to make this process work and make it economic. So what does the opportunity look like specifically in California? So this is a map from the U.S. Geological Survey showing where there are ultramafic rocks and mafic rocks, mostly at the surface in California. So you can see, most of the opportunity is in the northern part of the state, but really you have these types of rocks occurring all across the state, and even those blobs that look like, they're kind of smaller blobs, the removal potential associated with even those small blobs can be very enormous. So to put it in some concrete numbers, there are about 40,000 square kilometers of mafic rocks at the surface. There are about 5,500 square kilometers of ultramafic rocks at the surface. And so these combined have the potential to remove hundreds or even thousands of billions of tons of CO2, remove or store. We'll get into some of the details on that. So carbon mineralization, kind of like direct air capture, has different flavors. So they kind of fall into three main buckets. One is below ground, so referred to as in situ. So this is very similar in concept to traditional sedimentary geologic storage of CO2. You pump the CO2 underground, the CO2 reacts with the minerals there to form those carbonate minerals and store it permanently. The second category is called ex situ. So this is a more highly engineered process. So essentially, you take those appropriate rock types, you bring them to some sort of reactor, and then by increasing pressure and temperature, you speed up that reaction, combining it with CO2 that's been captured through some other process. And then the third broad category is often referred to as surficial. And so this is where, rather than taking the rocks to the CO2, you take the CO2 to the rocks. And so things like mining waste or industrial waste will react with CO2 in the atmosphere, or in the category of what they call enhanced rock weathering. You could take this rock material and spread it on things like agricultural fields or things like that. Basically, you just need to increase the contact of the rock with the CO2. So we are looking at research in a lot of these different areas, as are a lot of different organizations. But I'm going to talk specifically now about a project that we're doing in California that's in this surficial category, where we're using mine waste to try and speed up this natural process. So as I've discussed, carbon mineralization is a promising method to remove CO2 directly from the atmosphere. But most of the work to date is at the bench or small field trial scale, and so larger scale field trials are really crucial to advancing the field. This is one of those roads not traveled in our roads to removal report because there's just simply not enough data available to assess it at the same level of those other technologies. But we and a lot of others are doing research to try and advance the science. So California actually has an ideal site for doing these sorts of field trials. It's a serpentinite rock-hosted former asbestos mine in San Benito County called the King City Asbestos Corporation, or often referred to as the Joe Pitt Mine. So you may ask, why in the world would we go mess around with a bunch of asbestos? And it's for a couple reasons. One is that KCAC and this kind of deposit that it's in general is sort of unusual. It has a really high percentage of these short fiber, extremely unusually high surface area mineral called chrysotile. Chrysotile is the asbestos mineral. It's kind of an unusual deposit in that sense. That high surface area can be helpful in speeding up that reaction. But the real reason we're here is for a mineral called brucite. Brucite is a magnesium hydroxide. It reacts with atmospheric CO2 super quickly. It can completely react within days or even weeks under ideal conditions. And the KCAC and the broader New Idria serpentinite have an unusually high proportion of brucite, at least according to the literature, that's what it said, up to 25 weight%, which is kind of unheard of in these types of rocks. And third is because we see that carbon mineralization is happening naturally. These carbonate minerals and things called hydrotalcites, which also incorporate CO2 in their structure, we see them forming at the mine. So our objective is to go out there and to test multiple approaches to accelerate that CO2 mineralization reaction, while of course providing a very tightly controlled monitoring and safety environment, because this is asbestos. So the project is broken into two phases. We've completed phase one, so I'll go over some of the results of that. And basically what we wanted to do was just characterize the site and confirm, is this really an optimal location to do this? Is what we saw in the literature about the amount of brucite, is that really there? This mine has been closed for about 20 years. And so is there any reactive material left in these mine tailings? Is it actually drawing down CO2 or is it releasing CO2? Is this really a good place to do this work? So we kind of take two different broad approaches to trying to characterize what's happening naturally at the site. And one is to measure that question of, is CO2 being released or is it being taken up by this material? And we use a couple different methods to do that. One are these soil flux chambers that you see kind of on the left-hand side. This is a little chamber that seals over the soil. We have a little army of them set out there, and they're all automated, so they close on some regular schedule. They measure the air that's in that little chamber. It tells you how much CO2 is in it, and they just keep doing that over time. And then we pair that with another measurement called eddy covariance. That can measure a larger area, so those little chambers are just giving you that one little area. The eddy covariance covers a much larger area, and essentially what we want to see is those two systems agreeing. So if we see that both of them are showing CO2 release or both are showing CO2 drawdown, we feel pretty confident that we know what's actually happening there. So in that graph on the bottom, you can see the results from the eddy covariance monitoring. If I showed you a graph of the soil flux chambers, it would look like the same thing. So that red line that you see with the high oscillation frequency is the CO2 flux over time. And so when the red line is above that black zero line, that means CO2 is being released. When it's below that black zero line, it means CO2 is being taken up by this material. And then that black line that kind of goes from the left down to the right is the cumulative flux. So over time, over the 5 months of 2022 that we measured CO2 out there, that shows what was happening. So actually what we found is that CO2 is being taken up by this material, which was a bit of a surprise to us, and at a rate that's relatively high, about a kilogram of CO2 per square meter per year. And if you extrapolated that over the whole mine, that would equate to about 500 tons of CO2 per year. Not a lot, but in this context, it is kind of a lot. So that was great. Basically what that tells us is there is still reactive material out here, and it is actually drawing CO2 down naturally on its own. And then we paired that with doing a lot of geochemical analyses of the material that's out there, because we wanted to confirm, again, is there really brucite out there in those quantities, and has it all reacted, or is there still reactive material out there we can use? And what we were able to confirm with the geochemical analyses is that, yes, there is still brucite out there, there's still unreacted brucite, and in some cases we do find it in those really unusually high quantities, up to 25, or in this case what we measured in one of our samples, up to 24 weight percent. So basically what phase 1 confirmed, yes, this is a great place to do this work. There's reactive material, it's still reacting. We did some other work to confirm that it is actually atmospheric CO2 that's being incorporated into these minerals using radiocarbon dating. And so, yeah, we've confirmed this is a great place to do this work. So phase 2 is where we'll actually go out into the field and test these different methods to accelerate the rate of carbon mineralization. We're hoping to get that started this year. So we're going to be testing 2 different methods. Method 1, which is being led by Dr. Corey Myers at Livermore Lab, is what we call the greenhouse method. So as I mentioned, one of the challenges for carbon mineralization is you just need to find a way to increase the contact of CO2 with the rocks. And the easiest way to do that was with surface area. But in order to spread this material thin enough, in order to get the contact that you want, you would take up a really large area of land to spread it thin enough. And so Corey's idea is that rather than go out, you go up. So you can spread it in really thin layers on tarps or on trays, and then you can stack those trays on top of each other with sort of an ideal gap between them. You put those all in a greenhouse where you can also control all the ambient factors like temperature and humidity, heat, all those sorts of things, and you can optimize that reaction, but while still having essentially very little energy input, so you're not penalizing your CO2 removal. With some of those more engineered methods where you're heating it up or adding pressure, you're getting CO2 penalty for doing those things. So this is still a mostly passive, but more idealized method. And this would be a method that you would use if you were mining this material for purpose. So like if you wanted to create a company to pull CO2 out of the atmosphere, this would be the technology, this would be the idea. The second method that we're using, and this is in collaboration with our partners at the University of British Columbia, this is Dr. Greg Dippel's lab, the Carbon Lab, is what we refer to as the tilling method. So again, the idea is just to increase the contact with air and water with this material. You can see in the upper left picture, this is how mine tailings are normally stored. They're in these big piles. You don't really get much infiltration of air or water into the pile, which is what they want. That's how it's designed. But because of that, you're not getting the mineralization potential. So what this method would do is, as that waste material is sort of stacked up, you would just essentially drive like a tractor with a tiller attached to it over it to churn it up and increase the contact with air and water. The next layer of mine waste would be laid down, and you'd repeat that process over and over again. So what we plan to do at the site is we'll have our main tilling pile where we conduct this tilling with some frequency based on like the rate of the reaction that we're seeing. We'll have a control pile where we can measure, okay, what's happening in the background so we know how much we're increasing it over what's happening naturally. And then we'll have a couple, hopefully, of little control piles where we can vary things like what's the ideal water saturation, what's the ideal particle size, what's the ideal depth to which you should till it to increase the reaction rate the most. So we will be, as I said, hopefully starting that work this summer. And hopefully have some exciting results to report. We think we can increase that natural background rate by at least 2 to 5 times over the rate that we just see naturally. So with that, I just want to thank our sponsors and our collaborators, sponsored by the U.S. Department of Energy, Fossil Energy and Carbon Management, managed by the National Energy Technology Laboratory. As I mentioned, our partners on this are the University of British Columbia Carbon Lab, and the mine is actually located on land that's owned and managed by the Bureau of Land Management, who've been a great partner in this and facilitating the science here. So thank you. Happy to take any questions or to let you all go eat. Great.
Gotta make the exercise. Yeah. Can you hear me? Okay.
Yeah.
How you mentioned you were surprised when you saw that it was actually uptaking CO2 rather than releasing CO2.
Yeah.
How do you manage that tipping point in this whole process? What's your vision of how you manage that tipping point and oops, I'm now releasing CO2 rather than collecting CO2?
So yeah, I mean, I think also if we had maybe measured over a longer period of time, you might have seen that cumulative line like bump up a little bit. We measured this during the summer, and so it may be that, yeah, over longer time scales you actually see release. But when we're engineering the process, essentially once we know that those carbonate minerals or minerals containing CO2 have been formed, those are then going to be separated and placed in a situation or a containment where you can't reverse that reaction. It doesn't want to reverse naturally anyway. It's thermodynamically uphill to do that. So those minerals are very stable at the surface. But essentially, yeah, there would be a system for managing them after the carbonates have formed so you don't accidentally, reverse the process.
Thank you.
Yeah.
Thanks, Briana. Have you looked at the energy balance on, especially on the very active, using, let's say, tractors or to till it, and the amount of energy you use in that and the amount of CO2 that you release in that operation?
We have, so Corey Myers also did an initial TEA and LCA analysis along with someone else from our lab, Hannah Goldstein. And so both of these methods at commercial scale over 30-year levelized costs are both carbon negative. The greenhouse method is a bit more efficient. And if you, or I can send out the link that was on the end of the presentation, it has all the TEA and LCA information. But yeah, they are both net negative. The tilling method, as I said, is a little bit less efficient than the greenhouse method. And they both can reach a cost of less than $100 per ton.
Thanks, Briana. So my question is, I came in a little late, so I may not have caught this part, but at least with the initial numbers you have right now, how much surface area of rock do we need, like either subsurface, on the surface, tilled or otherwise? I mean, if you add up the total amount of rock surface being brought into contact with CO2,
Yeah.
what are we talking about surface space-wise to make a meaningful dent in the amount in the atmosphere?
Yeah, I mean, to do it just like with spreading it thin enough in order to be able to like ideally react it, it would be an enormous land area. And so I think that's why, we're looking into methods where you can take advantage of vertical space, things like that. But, the potential is enormous. If you completely carbonate these rocks, you can remove about 0.4 tons of CO2 per ton of rock. So, there's a large potential, but yeah, that's where the optimization and looking at all these different methods comes into play is how do you reduce the land area or the surface area that would be needed to actually achieve those idealized carbonation rates. Yeah.
Hi, this is Carolina Wilshire with Ana Kappa. Sorry, I'm keeping everybody from lunch, I know, but just a chemical engineer type of question. Have there been any tests with increased pressure and temperature? I'm just imagining like a column with change in media. Oh, I'm getting my picture taken. So has there been anything like that instead of thinking just atmospheric pressure, long surface? I can't imagine the amount of surface you need. It's huge, right?
Yeah.
Thank you.
Yeah, for sure has been. That would fall into like the ex situ category of carbon mineralization. And so, yeah, it's absolutely been done at the lab scale. The issue that faces is actually getting to net negative because of the energy inputs associated with the increased pressure and temperature. Both the costs in terms of like dollars and CO2 have been too high to pursue those methods commercially. But yeah, I mean, hopefully there could be a breakthrough in reducing the energy penalties associated with that because yeah, obviously that would really speed up the reaction. Thank you.